Welcome to today's Unit 1 introductory lecture. Before we really get into the heart of the unit, let's get some vocabulary words out of the way. Our first vocabulary word is magnitude. This is the size or value of a variable. This is basically the number with the units, but it's basically how big that variable is. Is it 10 meters? Is it 45 feet? Is it 1,000 kilograms? It's the number, the size. That's the magnitude. Two different types of variables basically that we will have in physics. The first one is a scalar. A scalar is a variable that has only a magnitude. It's just a number. A vector, on the other hand, is a variable that has a magnitude and a direction. So it has both a number, but that number says it's also moving in a specific direction. So an example of this would be 75 miles per hour would be a scalar. But if you changed it, 75 miles per hour northbound would now be a vector. Please make sure that you include some sort of picture or reflection on these three vocabulary words on the left side of your lecture sheet. Today's key word is vector. A little bit more vocabulary. Reference point. We talked a little bit about this today in class. A reference point is an arbitrary point chosen in space to represent a zero non-moving point. That point is basically the 0 point. Everything else around there could possibly be moving, but for the sake of your particular experiment or your study, you're saying that's basically the point you're focused on, and everything else is moving relative to that particular point. If we chose not to choose this reference point, we just wanted to say, figure out the speed of a car moving down the 15 freeway. Well, we'd have to not only measure the speed of the car moving down the 15 freeway, we'd also have to include the fact that the Earth is also rotating. So we'd have to include the speed that the Earth is rotating so that you now have the speed of the car moving plus the speed of the Earth rotating. Don't forget that the Earth is also revolving or orbiting around the Sun, so you have that speed as well. So now you have three speeds you have to add together to find the speed of the car. And of course, the Sun is also moving within the Milky Way. The entire Milky Way is orbiting. And in addition to that, the Milky Way is also accelerating throughout the universe since the Big Bang is exploding. Now, do you really need to do all of that, which is so much, just to figure out the speed of a car on Earth? Well, these other motions, do they affect that speed? No. That's why we set a frame of reference. And a frame of reference is a system for specifying the exact location of objects in space and time. So we want to focus down on a specific frame of reference so that we don't have to factor in all these other little pieces. We just want to know the motion of that object relative to the reference point within this particular frame of reference. That's typically either on Earth or even just in the classroom. What's the movement in the classroom of some particular object? We have to focus it down. If we don't focus it down, we just have too much stuff that we have to consider. Those are also vocab words. Reflect on those on the left as well, please. So now, let's get into the heart of the matter. First two things we have, two new terms that we have for this unit is displacement and distance. Don't mix these two terms up. They're most definitely not the same thing. I have an example here which I'll come back to, but first let's take a look at the displacement. Displacement is represented by the variable x, which is measured in meters. Again, it's in parentheses, so it's a unit, not a variable. Don't mix these two things up. Don't say that displacement is m. It's not. Meters are m. Displacement is x. Displacement is the total change in position. Total change in position. How we write this is just like this. We write delta x. This is the Greek letter del. Yes, it's just a triangle. But it has a specific meaning. Whenever you see this symbol in your head, you should think the words change in. So this is change in position because x is position. It's not the change in x, it's the change in position. And a change in position can be calculated by taking your final position and subtracting wherever you started. So if your final position is 10, but you started at 2, then your total change in position will be a positive 8. Okay? Let's go to distance is represented by a d, and it's also measured in meters. We will almost never use this, but it's basically just how far an object has traveled. So let's look at this example. You're coming from your house and you're traveling to school, and then you're going to go back again. That distance is 5 kilometers. So your displacement, though, is your total change in position. So you started at home, you went to school, and you came back. So you started at 0, and you came back to 0. So is there any displacement? No, because your final position is 0 minus your initial position is 0, says that your total change in position is still only 0. Distance, on the other hand, is how far you traveled. So that is a positive 5, and then you traveled another 5 kilometers, so the total distance you traveled is a total of 10 kilometers. What this means is displacement is a vector and distance is a scalar. Displacement takes into account direction. Here you moved forward, so that would be a positive 5 kilometers. Here you moved backwards, so that would be a negative 5 kilometers. Distance is just a scalar. It can never be negative. It doesn't matter what way you're going, you always add it up. So 5 plus 5 gives you a total of 10. That's distance and displacement. So in class today, we did a graphical analysis of what these two things represented. Like I said, we're going to focus on displacement. So we created a graph of displacement versus time. And what we wanted to figure out, the relationship, is that slope. So if you recall from Icky Math, you remember that to find the slope of a line, you take 2 points and you take y2 minus y1 and divide by x2 minus x1, and that's going to give you your slope. So let's plug in the terms that we're using into those places. Your slope is your rise over run. So you choose your 2 points, just like you did in math, but now my points are going to be my final position and my initial position. That final position has a corresponding final time, and my initial position has a corresponding initial time to it. So at the initial time, you were at the initial position, and at the final time, you were at that some particular final position, or where you started and where you ended. So we're going to plug those in. Remember, it's your y2, so that's your x final minus your x initial, divided by your time final minus your time initial, will give you your slope. Remember from the previous slide for displacement, x final minus x initial is your displacement. That's your change in x. Or this difference that you're going to calculate, final minus initial, will give you this value right here. That's how much x has changed. And you're going to get your change in time. Remember, the symbol del means change in. So your change in time is this value right here. How much time has passed while you moved that particular distance. So displacement is a vector. It depends on the direction you travel. You also could be traveling backwards, okay? Because your your position is a vector. You could be a positive or you could be a negative. Some of you started in a negative position in your lab today, so your position, that negative, meant you were behind your reference point. So that in fact had a displacement. It was negative. Remember, like I said, your distance can never be negative, but your velocity can be, or your displacement can be. So your position can be negative. We give this term a special name. This change in position over change in time, we give the special name velocity. Distance over time is speed, but change in position over change in time, your position is a vector, your displacement is a vector. Therefore, we have to use a vector quantity, which is a velocity. And your velocity, if your change in position is measured in meters, and your change in time is in seconds, then you would have a meter over a second. So your velocity is measured in units of meters per second. Remember, the triple dots in a triangle means therefore. So velocity versus speed, what exactly is the difference? Well, speed is the rate at which an object travels. So the speed would simply be how far you traveled over how long it took you to get there. And that would just be a scalar. It doesn't matter which direction you moved. Velocity would be the rate an object travels in a specific direction. So it's your change in position over your change in time. Of course, speed is a scalar, velocity is a vector, but both of them are still measured in meters per second. It's whether or not you give a direction that determines if it's a vector or a scalar. So going back to that same example, starting at home and going to school. Let's say that it took you 100 seconds to do that. So to travel there is 5 kilometers, and to travel back is 5 kilometers. That's a total of 10 kilometers. Remember, there's 1,000 meters per kilometer. So this would be 10,000 meters. And we said that it took you 100 seconds. So you would have 10,000 meters divided by 100 seconds would mean your speed would be 100 meters per second. On the other hand, your velocity, well, if you start in that position but you return all the way back to that position, then your net change or your total change in your position is 0. And it doesn't matter how long you took, it's still going to be 0 meters per second. It's going to say you didn't actually go anywhere, basically, because you returned back to your starting point. Remember, if it's a 0 on top, then the answer is 0. It's when you have a 0 on the bottom that it's undefined, which doesn't happen naturally in the physical world, so you should never have an undefined answer. Let's look at another example. Okay, here we have a kid on a skateboard, and he's going to start at a position of -2, and he's going to travel forward to a position of +2 seconds, and it's going to take him 18 seconds. So our velocity would be our change in position, or our x final minus x initial, divided by our change in time, our t final minus t initial. So our initial position, or our final position, x final, is at 7. We're using the back of the skateboard as our reference, or as our measurement point, so we use the same method in both cases. 7 minus the initial position, which was -2. So 7 minus -2, negative and a negative makes us a positive, which gives us a 9. And it took 18 seconds, so there's our 18. So it's 9 divided by 18, and this is measured in meters, and the time is measured in seconds. So if we simplify this, we get 1/2 a meter per second is this boy's velocity on this timeline. See you next time in class.